Hey guys, Mr. Martin back here again with today's video on how to prove triangles congruent by SAS and HL. SAS, of course, standing for side angle side, and introducing you to a new one you may have not heard of called hypotenuse leg. Let's get started. Alright, before we start talking about side angle side, I want to introduce you to a vocabulary term called the included angle. So we're going to talk about the angle that is included in between two sides. So consider a relationship involving two sides and the angle they form. So if we look at the first triangle, if we look at side AB and side BC, obviously the included angle is angle C, or angle ACB. So between sides AC and sides BC, the included angle is angle ACB. Okay? Let's do another one. How about with triangle DEF? Let's do sides DE and EF. It's obviously going to be angle DEF. So for sides DE and EF, the included angle is angle DEF. Okay, let's do one more. Just so you get a really good definition of what the included angle means. Let's try GI and IH. Okay, so between angle or sides GI and IH, the included angle is GIH. Oops, not GIE, but GIH. Okay? Alright, so make sure you got a good definition of included angle. Alright, so I want to show you the side angle side postulate using some pencils. We can learn a lot from some pencils, believe it or not. So anytime you form an angle of the same measure with two pencils, so in other words, you take two pencils and you open them up to, let's say, a 24-degree angle. The side formed by connecting the pencil points, so we're going to connect the pencil points, okay, will have the same length. So if I take two pencils that have the same length and I open them up to a 22-degree angle, obviously the ends of the pencils will make a segment that's going to be the same length if this is a 22-degree angle. Okay? Obviously, the more you open that up, the distance from the endpoints of those segments or the tips of those pencils will get bigger. You close up the angle, it'll get smaller. So obviously, every time you open it up to a 22-degree angle, it's going to have the same distance from the tips of those pencils. Kind of makes sense, doesn't it? So I offer that to show why the side angle side congruence postulate works. The side angle side congruence postulate basically says if two sides and the included angle, there's the vocabulary we just talked about, the angle between the two sides, okay, included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. So you got the first triangle with RT being congruent to UW on the second triangle. You got RS from the first triangle being congruent to UV on the second triangle. And you see the angle in between, or the included angle. You can think of in between, also known as included, the angle in between. Okay? So let's go ahead and use this. Okay, just a quick proof. Got two triangles here. Looking at the two triangles, I can see that they share that side in the middle. Got some parallel lines, so I see some alternate interior angles being congruent. And I also see another pair of alternate interior angles being congruent. Okay, but let's just use the first pair. Okay, so we don't need this. We don't really need that second pair, because once we have two sides and the included angle, we are done. Okay, so we're going to use just one of those pairs of. Okay, so the first obviously is the given. That's kind of a no-brainer. Okay, they gave us one of the sides. Okay, they told us that BC was congruent to DA. BC is congruent to DA. Okay, we already noticed that angle BCA is congruent to angle DAC. Okay, and then we notice that side CA is congruent to side CA. So we have, if you notice over here, we're kind of keeping track of what we have. We have a side, an angle, and a side, and we have the included angle. So we can say that those two triangles are congruent using the side angle side congruence postulate. Pretty easy. All right, let's keep going. Okay, I want to introduce you to the donkey postulate. This is actually a postulate that does not work. Let's explain why. It says in general, if you know the lengths of two sides and the measure of an angle that is not included. This is why it's so important to know what included means. This time, if it's not included, if it's not in between them, you can actually make two different triangles. Okay, so obviously, if one person picked one of the triangles, it would not be congruent to the other triangle if the other person picked the other triangle. If you can make two different ones, you obviously can't say that those two triangles are congruent because they're different. Therefore, side-side angle is not a valid method for proving that triangles are congruent. Although there is a special case, we'll talk about in a little bit, that does apply to just right triangles. That's the only time it applies. Okay? So generally, it does not work. Okay? SSA is a big no-no. Let me show you what I'm talking about. Okay? We have two triangles here. Okay? You can see we've got BC being congruent to BC. Okay? We got AB being congruent to AB. Okay? We got angle A and angle A being congruent to each other. Notice we don't have the included angle. Okay? You obviously can set AB and AC at a certain angle. AB and AC are set at a certain angle. That angle is staying the same. You can see, though, that we can swivel angle B right here, okay, and the segment BC will touch an extension of AC at two different places. In the first triangle, it's touching somewhere about right here, and in the second triangle, it's touching somewhere out there. Okay, so if you can imagine that swiveling at angle B, then you could see that it would actually hit two different places. Think of it just kind of swiveling and then going back and hitting right there. Okay, so that's why we say the donkey postulate does not work. He's one of my favorite characters from Shrek, but unfortunately, his postulate doesn't work. Okay, all right, let's keep going. Let's talk about that special case that we mentioned just a little bit before. In a right triangle, the sides adjacent to the right angle are called the legs. Okay, so here's our right angle. You guys know that the right angle is the one that's got the box in it, right? So here's our right angle. The sides that are adjacent to that right angle, or in other words, the sides that make that right angle, those are called the legs. Okay, so these are the legs. If they're not the legs, if they're not the adjacent, then they're obviously called the hypotenuse. You guys know hypotenuse from probably 6th or 7th grade. It is the longest side. It is the side that is opposite the right angle. That is the hypotenuse. All right. Just some vocabulary. If you don't know that vocabulary already, just make sure that you get that vocabulary into your notes. Okay? Legs and hypotenuse. All right, so boy. Okay? The HL, or hypotenuse leg congruence theorem, says if the hypotenuse and leg of a right triangle are congruent to the hypotenuse and leg of a second right triangle, then the two triangles are congruent. This is that special case that we talked about. It only works for right triangles because you notice now we've got two sides and an angle not included. It will only work for the right triangles, okay? All right. Look at an example of this again. Again, we got two triangles here. They tell us a whole bunch of given information. They tell us that WY, if you're not marking up your pictures, you should definitely be marking up your pictures. If you can see from this one, it's a little difficult to mark up this picture. So you know what I'm going to do? It's okay with you guys. I'm going to separate the two triangles that we're talking about. W, Y, Z. Okay? And then we got triangle X, Z, Y. Now we got those separated. We can actually mark them up. Let's mark them up. Okay? WY is congruent to XZ. Okay? WZ is perpendicular to ZY. Okay? And XY is perpendicular to ZY. So if you're trying to mark those up on this picture, it would be a little difficult because how do you mark, WY and XZ? That looks like only a little part of that is marked up. So sometimes it's easy if you just separate the two triangles. Let's go through a proof of this real quick. Okay? There's a suggestion again. Separate the triangles. Mark up the new diagram. Okay? Alright, so the first statement, you guys know as well as I do, always restate the given. Bring the given information into your proof. Notice here they're using two statements. I say that one statement would be okay. Okay? If you only used one statement, that would be okay. But they're doing it in two because there's a lot of information and there's really two separate pieces of information. One is giving us obviously a side being congruent. The other is giving us a angle being congruent because we know that all right angles are congruent to each other. And when those two sides are perpendicular, they form right angles. Alright, let's keep going. Okay? Right angles because of the definition of being perpendicular. We know that they're right triangles because they have a right angle. Okay? We know now, one thing that we did mark in our diagram was that that bottom side that they both share is obviously congruent to itself. There we're starting to see a real use for that reflexive property, right? It's like, why do we care that something's congruent to itself? Of course it is. Well, anytime the same segment is getting shared between two of those triangles, or the same angle is getting shared between two triangles, we're always going to say that they're congruent to each other using the reflexive property, because anything is obviously congruent to itself. Okay? And now you notice over here they're keeping track of, we got the H from the given, we got the L because we knew that it was a they were sharing that base, and now those two triangles are congruent to each other thanks to the hypotenuse leg congruence theorem. Well, there you go, guys. That was the side angle side and the hypotenuse leg congruence theorem, and we did that in under 15 minutes. Okay? Get that into your notes. Have a great day, and we'll see you in class.